Welcome everyone to this event in our long and fantastic Encode Tezos series. Today we are going into the depths of smart contract development, building dApps, really getting into the nitty-gritty and really being extremely applicable to when the hackathon stage starts in a few weeks, of which we'll properly announce very shortly. Because I'm sure a lot of you, after having done all the hard work in this learning process, want to put that to good use in building some applications. We're delighted to have John and Dani back with us today to talk in depth about that fantastic topic I've just mentioned. And I hand over to both of you now to take us through the whole process. Thank you very much and looking forward.
Thank you. Right, so before we have talked already about the technical background of developing on Tezos and touched on quite a few things, this presentation was mainly envisioned as an introduction to smart contract development for dApps specifically. Now, I would like or envision this presentation as a bit differently to how these Smart Contract 101 presentations usually go, because ultimately, if you can already code, then you can code a smart contract. It's just programming. Some blockchain platforms use languages that we use in other situations, like some of them use WASM as their blockchain virtual machine, and that means you can write the smart contracts in Go or Rust. So there's nothing fundamentally special about coding smart contracts. Only the approach, the way we think about designing a smart contract is fundamentally different than the way we design or think about a more traditional computer program. It requires a fundamentally different mindset, even though the tools we use are very similar. And so this 1 hour is dedicated to talking about this difference and how one should think about designing a smart contract. Now, since we only have 1 hour, I am not going to be doing any code examples today. That would add a lot of time and fiddliness. And also, I would like these learnings from today's presentation to be more portable and general. And I kind of hope that non-coders who might be here today can also glean things from this presentation. I'm pretty sure that, for example, someone who is designing the user experience for a dApp might benefit from knowing some of these fundamentals. And ultimately, if someone wants to go into the deep end of learning a smart contract language and looking at examples, there are some really, really good resources on the websites of the languages themselves. So again, what is a smart contract? So a smart contract is a code that in our case runs on a blockchain and it implements business logic restrictions. So as we mentioned in a previous slide deck in a previous presentation, there is this famous metaphor from Nick Szabo, who is a researcher in the field of smart contracts. The smart contract is like a soda vending machine, or more, a soda vending machine is in a way a smart contract, in the way that the vending machine has soda in it and it has change in it. And if I buy soda, then I get a soda out of it and I get change. But my access to the soda and the change in the machine are limited by the logic of buying soda. So I have to put in money first, and it has to be enough to buy the soda. Then I get the soda and I get back the exact amount of change that I'm due. And I cannot just open it and take out all the soda, for example. So that is a smart contract. It realizes a set of business rules about a transaction. Smart contracts on a blockchain, on a public blockchain, are defined by an interface of callable functions. These are the things that one might be able to do on a smart contract. So if we look at the soda vending machine, if it was a blockchain contract, it would have a function which is called buy soda, and it would have a function which is called refill. And of course, refill would only be able to callable by the operator, while buy soda can be called by anyone who can pay for soda. These callable functions can be called either from a wallet address, what in Tezos we call an intrinsic address, or from another smart contract. However, it's very important to understand that all chains of calls are ultimately initiated by a wallet, by an intrinsic address. So anything that happens on the blockchain is kicked off by someone or something off the blockchain. And also, since the security of smart contracts is uh, is ensured by all nodes of the blockchain, all the computers running the blockchain, being able to execute it and validate that whatever operations and state changes were made are valid and uh, and compliant with the code that is on the chain. This means that everything that a smart contract does needs to be deterministic. And of course, this means that generating randomness on the chain is either impossible or at least very hard. So, or I would actually say that generating randomness on the chain is just downright impossible. And it is very hard to get randomness on the chain. There are ways of getting there, but not very easy ones. This is something that people keep asking because, of course, if someone's designing a game, for example, then randomness is a very common requirement. And as long as we're inside a smart contract, we're on the chain, it's also extremely hard. Another thing about coding with smart contracts is that we need to think with very limited resources. So I'm saying we're programming like it's the 50s, but probably it's even worse. So in the 50s, you could actually say that, oh, I'm going to loop over this list. And maybe it took a day or two for these IBM, punch card machines to run through the loop, but it would run through eventually, but not so with a smart contract. So with smart contracts on the chain, both the time that you can spend running your code and the amount of memory you can use in your code are artificially bounded. That is, there's an artificial limit on it, and this is executed by this thing called gas on chain. That's measured. We're measuring how much time and memory a smart contract execution takes. The more it takes, the more expensive it is. And there's like a solid set maximum that once it reaches, the chain will consider that execution failed. And of course, you still have to pay for it, but it's failed. It didn't do anything. And the reason that this was developed this way was to protect from denial of service attacks. Because if you could just kick off a smart contract that gets in an infinite loop, and then all the computers on the chain spend like a lot of time in that infinite loop without realizing what they're doing, that would slow down or eventually even halt the entire chain, and we cannot allow that. So what this translates to when we're designing is that a smart contract has to have big O1 execution time and big O1 memory use. And what does big O1 mean for those who didn't study computer science? It is a mathematical notation, which means that no matter what like the size of the input is, the execution and the output needs to be, or the execution and the memory use needs to be within a constant limit. So Now, usually when we're talking of big O, we're talking of functions. So like big O n or big O n squared or big O e to the power of n or something like that. And so when we say big O1, that's actually shorthand. The shorthand for big O 0 times n plus 1. And this n is the size of the input that we're like linking this to. And what n is anything in the smart contract state that grows with continued use of the contract. So if, like, for example, what can grow with continued use of the contract? Number of users that have registered, the number of addresses that hold a certain token, the number of tokens that have been minted, the number of games or marketplaces that have been created. So like anything that can, like, with continued use keep growing, that can be n. So any of these parameters we need to be independent of in terms of our execution. Also, if we want to go into like some pedantics, so when we're talking about big O1, it's from the perspective of the so-called gas meters, or like the logical uh, expression of time and memory use on the blockchain protocol. In reality, when we're looking at it from the perspective of the CPU that executes all of this, it can actually be like a big old log n, for example. So it won't always be really, really big O one, but that's all right as long as like the gas meter, as long as the protocol sees it as big O one. Now, there's a thing on Tezos that's important to this, is that on Tezos, uh, when we are deserializing or serializing storage, that is loading or saving storage back, um, it counts toward gas use. So the larger the state of a contract is, the more gas it will use. We have a special data structure called Big Map on Tezos that was specifically created to sidestep this. But as long as you put anything outside a big map, you are running a risk of, if you're growing that state, you're running a risk of having the gas use grow. And one example of this was the Tezos NFT drop.
Sure. So yeah, there was one very entertaining success disaster on the Tezos blockchain when these extremely popular generated NFTs called Tezos were minted. And they were enormously oversubscribed, but there was a design flaw in the smart contract. And the design flaw was simply this. Every time a Tezos was minted, an entry was made in a map. And every time the contract was called, the map was loaded into memory. So every time the contract was called and an entry was added, the contract got a tiny bit more expensive to run. When this happened for the first time in a block, it was absolutely fine. But when the second call happened, the estimation was based on the contract's previous size, and it was an underestimation. And so the call failed because there was not enough gas on. And I mean, the launch succeeded. The Tezos were extremely popular. Maybe they were even more popular because people had to wait for them. But there was a period of examination afterwards where we all tried to work out what had gone wrong. And in fact, Dani identified what the problem was. And the problem was that the operation was not O1 because it depended on the previous executions on the contract. So the solution to this would have been to use a big map rather than the map. And a big map is a special construct that was added to the Tezos blockchain after it had initially launched in order to prevent exactly this kind of problem. A big map is a map, a dictionary, so a key value store, but it's only lazily loaded. So you only pay gas for the records which you explicitly access. But of course, with every advantage comes a cost, and the cost of a big map is that you cannot ask on the blockchain what all of the members of the big map are. So you can get values out, but you cannot tell all of the values that are in there. So no on-chain iterability. Yes, so, but I saw a loop in. Of course, there are times when you have to loop, and they may be things where you know that there will only be 4 elements, or you know that your thing is initialized at storage to 5, and those 5 are all the ones that will ever be in there. So you're allowed to loop over user input because the user can split the list if it's too large. So for example, with an FA2 contract, we give a list of instructions to the contract. We say transfer to this address, this address, this address, and this address. But the user decides what that list is, and the user pays for the gas. So in this case, it's acceptable to loop over the user input. And as I said before, if we know that it's a fixed size in the storage, so we're splitting the revenue between 3 or 4 people, then again, it's perfectly acceptable to loop over it. Dani, I think you need to explain this edge case though.
Okay, so there is like a situation where we know that a list will be bounded, but it's not fixed in size. And this is exactly the Tezos effect, because there was like only 4,096 Tezos minted or planned to be minted. So it was bounded. The number of Tezos didn't go into the millions. So in a way, this problem didn't result in the smart contract becoming uncallable, because if the Tezos would have gone to like the number of like into the millions, then eventually calling the Tezos contract would have become prohibitively expensive and eventually impossible, because it just surpasses the amount of gas that is allowed to be used in a single call. But since the number of Tezos was limited, it was still bounded. It was like not catastrophic. But at the same time, because it was growing with use, um, the amount of gas that was needed to run a call was dependent on the calls run on the contract before it, and this made gas estimation unreliable. So this is why looping over a bounded size list is workable, but it's considered an edge case. Like if you don't absolutely have to do it, then better not do it. So yeah, another thing about smart contracts is that they are set in stone. The reason we can trust a smart contract on the blockchain is that it is unalterably written onto the chain and signed, and all the executions are validated against this code that's on the chain. Now, this means that we cannot just go in and replace it with a new version, or at least not in any simple and easy way. So if the smart contract has bugs, we will have to abandon like if it has like serious breaking bugs, then we will have to abandon it and move to a new smart contract. But of course, this might or might not be possible. Like we need to organize the move socially. We need to put up with losing face with our users. And we might also end up with resources, that is money or NFTs, being locked in a buggy contract and impossible to be accessed. Now there is like a thing around that's called upgradable smart contracts, where we have like a logic on chain that somehow allows us to replace parts of the logic that is executed. So for example, we can save logic into a big map as a lambda, as a function, or we can redirect calls to another smart contract that can be changed. Now, this can be a solution in some cases, especially when the smart contract is just used for auditability by a centralized entity. But in most cases, it's not recommended because it means that whoever has the ability to do the upgrade has full control over anything, over the future of the smart contract. So if I put money in a smart contract and know that someone can upgrade it, they have full power to eventually upgrade the smart contract and steal my money in any way they want to. When you're building a smart contract, you're building a lock. That is, you're locking value, you're locking the ability to write information. So you need to always think about who would benefit from exploiting this smart contract. Who could steal money or value from it? How could this be done? And what can you do to make it safe against all the attacks that you have identified? If a smart contract is exploitable, it will be exploited. It's called a public blockchain because it's public. Everyone can see everything that happens. And there are people whose hobby it is to just go around and steal money from badly written smart contracts or just destroy them for fun. So if the attacker cannot profit by breaking the smart contract but can hurt others, expect someone to do it. They absolutely will. And people have done it. So like on the Ethereum, there was something called the parity hack. There were two of them. The second parity hack, the first parity hack, people stole money. In the second parity hack, no one stole anything. They just destroyed about 300 million US dollars on the Ethereum blockchain for fun, as far as we can tell. So what does safety mean? So security is so that no one can steal my money from my safe. Safety is that if my house burns down, my money will still be safe. Um, this is like the topic of guaranteed availability or censorship resistance. So if someone puts their life savings in a contract, can they rely on it being functional 10 or 30 or 100 years? Now, of course, the blockchain itself will live as long as it can live. But by the way, like with a proof of state blockchain, even if no one was baking for like 10 years or 100 years, and then someone got a copy of the blockchain and had like some baker keys, then they could just start baking again and it would kind of work. So the blockchain can be considered safe, yeah, but we also need to think about off-chain components, and this is especially a topic of interest with NFTs, like the actual images and metadata of NFTs and Tezos are usually stored in IPFS. So if you own an expensive NFT, you should have like yourself a backup of the metadata and the asset of the NFT, because if it's gone from IPFS, then you still have it. Otherwise, it can just go away and now it's worth nothing, more or less. So you need to think about like if you, as in like you, the person who wrote this smart contract, or you the company who are operating it, if you disappeared or went out of business, would the people with money or interest in that contract still be able to access their holdings? There are things called indexers, which we mentioned before. Again, this quote from Arthur Brightman, one of the early architects of Tezos. I really like this. So if 100 lines of code off-chain can save 1 line of code on-chain, I consider that a good trade-off, because code off-chain is so much cheaper than code on-chain in all manners of ways. So when we're writing smart contracts, we are aiming to be simple and straight to the point. And what an indexer helps with is that it indexes the blockchain or a few contracts on it for querying. So it's kind of like Google for your smart contract. Using an indexer means that your smart contract does not need to worry about searchability. It doesn't have to worry about usability. You can just focus on making your code simple, making your code resource preserving and secure and safe. I'd like to quickly walk through a, we're at halftime, so I think we can do this quite well. So I'd like to walk through a simple example. We're going to look at how we would design a rock, paper, scissors game as a smart contract. The flavor of rock, paper, scissors will implement will be a one round game of rock, paper, scissors with bets. So that someone makes a bet, another person also makes a bet, or matches that bet. So if I put down 5,000, then the opponent also has to put down 5,000. We play a round of rock, paper, scissors. The winner gets both bets, or the whole jackpot. But if we are like we get a draw, then we just take back our own bets. Rock, paper, scissors is a very interesting game. One of the reasons is that it implements challenge response randomness. So that means that two decisions from two individuals add up to a random outcome. And it's for this reason it's particularly interesting for blockchain games, because as I said, generating randomness on the chain is impossible. So any ways where we can like magic in some randomness is really interesting. But also it's very challenging to implement well, and we'll see very soon why. So let's look at a naive implementation of rock, paper, scissors. Now, these words you see in bold are like calls to the smart contract. So first, Alice says, I challenge Bob by betting 5,000 playing scissors. Then Bob, seeing this challenge, says, I match Alice's bet of 5,000 playing paper. And then Alice, seeing that she has won, says, I claim my win of 10,000. So to implement this in a smart contract, we would have to store Alice's address and Bob's address. We would have to store the bet amount, and we would have to store Alice's and Bob's move. And I would like to ask if anyone sees what's horribly wrong with this. Anthony, if maybe you can read things from the chat. Or...
So we have the suggestion that the problem is storing the moves.
Yeah, exactly. So since we're on a public blockchain, and Alice has stored her move as part of the challenge, that means if Bob is any level of tech wizard, he can just go into BCD or TZKT and look at Alice's call and know what Alice has played, and of course always play the winning move. So there is a solution to this, and that is by using masked moves for challenges. So a salted hash is generated by taking a message and concatenating, that is adding onto it a random string, which we call a nonce. And we take this like full concatenated string and hash it, and we get like a salted hash from that. So for example, Alice's move is rock, and then she concatenates this really, really long number string to that, hash that, and she gets this hash from here. And so the way the game would play out would be like this. Alice says, I challenge Bob with a bet of 5,000, playing the masked move of the hash of whatever this is. Now, Bob, because he does not know what the nonce is, has no way of figuring out what Alice's move was. So the only thing Bob can do is that he matches Alice's bet of 5,000 and announces his move. So what we don't actually need to mask Bob's move, but maybe we can talk about why that is later. Then once Bob has made his move, Alice says, I reveal my play of rock with the nonce 2, 4, 3, whatever. And this way, Alice is forced to reveal her actual move. She cannot say, I reveal my play as scissors, because she has no way of creating the same salted hash from a string that starts with scissors. That would constitute a successful attack against the hash algorithm that she used. And if we use a secure hash algorithm, that would take probably millions of years. So so Alice has to reveal her actual play. And then, since Bob now sees that he has won, he can go in and claim his win of 10 tasks. And this is called a commit reveal scheme. The reason Bob didn't have to mask his play is that masking by is that the using this commit, Alice was actually forced to reveal her move as her actual move. She couldn't change her move afterwards, so it didn't really help her that now Bob's move is open. But however, there's still something that we need to solve with this, and I wonder if there's anyone who sees what that is.
Certainly, Alice can decide not to reveal at all when losing.
Yep, exactly. And that is the next slide, actually. So, the way we handle this is we implement a time lock. So, if Alice is a sore loser and disappears after Bob has played a winning move, the smart contract can have built-in logic that allows Bob to claim his win by no-show after a certain timeout has elapsed. Usually, because blockchains work slow, these timeouts are not measured in minutes, but rather hours or days, so that if maybe there's congestion and Alice's move would be delayed by, for example, it not getting baked or getting lost in the mempool or something, Alice wouldn't be at risk of losing her bet. But if once like several hours have elapsed or maybe a day or two, then we can say with quite good certainty that there is a no-show situation, and the party who last played a move can now claim the jackpot. And this also protects Alice, because when Alice first issues the challenge, she already places the 5 tests down, and if Bob decides to never come in and play with her, Alice would have to be able to reclaim her bet, and having a timeout allows for that. Now, when we're talking about like how this looks and user experience, etc., I would like to talk a bit about how we distribute work in a distributed application. So you might ask, isn't this too complicated? Like having to have this really long random string that we need to remember. It has to be generated, it has to be random, it has to be remembered and stored. So it's really, really complicated for a human. So wouldn't be a lot of fun to play this game in its raw state. However, that is what the off-chain part of a distributed application is for. So the only purpose of the smart contract, as we mentioned earlier, is to make things secure. It is to be the lock on the door. All the convenience can go off-chain, and that is where all the UX design should come in. Like, where should we store this nonce? Should we store it in browser local storage? Should we have the user write it down on a paper with a pen, etc.? That's all UX design, and it's something that I believe will be the part of the topic of the next presentation. So if we put it together, with this smart contract, where one smart contract just handles a single round, single game, what would the interactions look like? So first, issuing the challenge. In this case, it's not a function call. It is the deployment of the contract. The challenger deploys the contract with the challenge details written into the storage. Now, there's like a thing here that the challenger could send less tasks or initiate the smart contract with less tasks than what they claim the batch sizes in the storage. Now, is this an issue and why not? Maybe if someone could mention that in the chat. No,
No answers so far.
okay, so the reason it's not an issue is that Bob can actually look at how much TAS is in the smart contract. So if it says that the batch size is like 100 TAS and there's one TAS in the smart contract, that means Bob could only join the game with 100 TAS, and that wouldn't be like a good game. So Bob will just decide not to join at all. So since it's a public blockchain, these kinds of deceptions are really easy to uncover. So this is not an issue that we as the designers of the smart contract need to worry about. Though when we are designing the front end, the user experience, it might be worth maybe showing the actual amount of tests in a smart contract. Then the second call would be matching a bet. This is only callable by the person challenged in the challenge, and they match the bet and play their move. Now, this function can actually verify if the challengee is matching the bet with the exact amount of tasks that it's supposed to be. So Bob cannot say that, oh, I'm just sending 5 tasks for this is 100. Then another function call would be reveal. This is where Alice reveals her play. Now, the, as parameters, this call would take the move itself and the nonce, the salt, that is this random string. And one thing that this function will do is validate the move and the salt against the saved commit hash that we already had stored. And this way Alice cannot lie about her move. The Mikkelsen virtual machine in Tezos has built-in primitives for doing certain hash algorithms, so it's relatively easy to do this on the chain. And then the final call, and probably the most complicated, will be claiming the winnings. So this is the point where the prize can be claimed. If there is a clear winner, then the winner is allowed to withdraw the entire pool. If there was a timeout, then the player who made the last move can withdraw the entire pool. And if there was a draw, then both players can withdraw their pool. Now, what do we need to save in storage and state in order to implement all this? I wonder if we can collect it in chat.
So we have the nonce, the challenger hash, contract addresses who have played.
So first we need the challenger's address because we need to make sure that only they can withdraw their winnings because they were the one who put down the bet. We need the address of the challengee, that is, not anyone can take the challenge, only the person it was intended for. We need to save the bet amount because we expect the challengee to match that bet exactly. We need to save the challenger's commit hash, or once the reveal has been made, we can replace it with the move itself. And once the challengee has made their move, we need to save that. In the same field, we will store nothing until they have made their move. And finally, we need the last move's timestamp for the timeout functionality, and we need to save who the last move was made by so that we know who can withdraw the jackpot if there is a timeout. And we also need to store the timeout duration in some way. This may be hard-coded in the code, or it can be part of the storage. Is there anything that we still need? I wonder if someone can spot that. we need one more thing, and that is because we need to handle draws, and draws are a bit more complicated than just wins. Um, so when we have a draw, both players need to be able to withdraw their own side of the bet. Now, if we look at this amount of data that we already have in state, we could big brain out some kind of like way to figure out who has already withdrawn their half of the draw and who hasn't. Like, for example, we could just uh, null out the challenger's bet if the challenger has withdrawn their bet. Or so we can kind of hack this in the name of making the storage smaller. But I would say this is not recommended. Don't do this. We are coding a smart contract. We need to keep attack surfaces and possibilities for bugs to a minimum, and we need to keep the smart contract as readable as possible. So saving a few bytes might mean like saving a few cents, but it might also mean introducing a major bug that will lead to the loss of millions. We should just have a field that we are only using in the case of draws, and that tells us who has claimed their half already. By the way, this can also be an additional level of or layer of security for making sure that the winner cannot like withdraw more than once, even though with this smart contract where one game is only played, so one smart contract is only used for one game, that won't really be an issue. But once we go into the multi-game situation, it will be. So yeah, now we have to add the claims completed field, which would be non-challenger, challengee, or both. Deploying a new contract for each game was really made it simple to think about it and to design this logic, but it's quite wasteful. Deploying the code of a smart contract to the blockchain is probably the biggest single expense that you will have in a transaction. So that's not something we want to do a lot of. So how about we just extend our logic so that a single smart contract can handle multiple games? Now, the way we can do that is by using a big map. Of course, we cannot store all the games in non-lazy storage because that would kill the big O1 behavior, as we mentioned before. Um, but we can put the games in as records into a big map. And the the value of a record in the big map for a game would be the storage of the single game contract that we just defined. Now we also need to index this big map with a key. It's of course a key value store. One might be tempted to find a natural key to this, like the address of the challenger of the address or the address of the challengee, etc. But we want our code to be flexible. We want one person to be able to play multiple games at the same time. So I think it's better to go with an artificial identifier that is a simple whole integer number that uh, we can identify a game by. There might be a temptation to use an auto increment number. So the first game ever played will be game number 1, then comes game number 2, then comes the game number 3. I personally wouldn't recommend this. I strongly recommend using deterministic user supplied um, identifiers. So yeah, what does this mean? It means when I create a new game, I say I want to challenge John to a game of rock, paper, scissors. I will say that this game will be game number 65997999879, because and that's like any number I can come up with. I can that like the off-chain code can generate it from a hash of something. Like for example, if we're like in case of like an NFT smart contract, we can generate an NFT's ID from the hash, for example, or it can be just a random number that I just came up with. The reason this is better than having an auto-incrementing number is that it is deterministic. So at the moment I'm issuing the blockchain operation of creating a new game, I already know what the identifier of that new game will be. And of course, it might already be in use. Someone might like come in and just create a new game with the same ID before me. But if we have a big enough domain, then the chances of this happening are minuscule. And I don't need to wait for the blockchain to tell me what my ID will be. And this is especially important if a smart contract is used a lot. So if there are like, for example, multiple calls to it in the same block, because then, when I'm running the simulation of a new game call before a block, and then I would see that, okay, my game will be most likely game number 1009. But then there are, so it turns out that my game is the fourth new game operation in the block that it gets included in. Then it turns out that in reality, it will be created with the number 1005. So I need to like keep looking at the blockchain, making sure that it's right. I think it's error prone, and it makes it really hard for the people who are implementing the off-chain logic. So just go with user supplied identifiers. In what way do we need to change the interface of this smart contract? So of course, creating a challenge, creating a new game is now not a smart contract deployment. It is a function call. It takes a game identifier that, as I said, should be user supplied, and the game setup information, that is who I am challenging, and what my commit hash is. Now the bet amount in this case can be auto-filled by the smart contract by the amount of Tez I'm sending with this call. The smart contract can figure out, there's like a Mikasan command for seeing how much Tez is being sent with with this call, and then that can automatically be populated into the bet amount field. And of course, all the other operations will now take a game identifier along with their existing arguments to make sure that that the smart contract knows which game these operations will be executed on. And another thing that I believe is just good manners to do is clean up. So when you are using a big map and there is a very clear end of life for your big map entries. So for example, the end of life of a rock, paper, scissors game is when the winner has claimed their winning, or in case of a draw, both parties have reclaimed their bets. After this has happened, we should evict the big map record pertaining to that game. No information is actually lost here because the blockchain stores its history. So it's not like we're deleting data, we're just taking it out of the quick access memory of the blockchain and making it like just easier for everyone to run a node. And we're also making it cheaper for people coming after us to make calls to this smart contract.
We just had a good question. So why use a big map versus a regular map? And yeah, just to re-emphasize, so this was the same as the Tezos issue. If we use a regular map, then every game will be more expensive than the previous game. Whereas if we use a big map, the cost of the games remains constant no matter how many games there are. So it's just this thing of having good manners on the blockchain and making sure that everything we do is O1.
Yeah, exactly. And eventually, if we don't use a big map, if there are too many games, then the smart contract might become uncallable because calling it would take more gas than what is allowed in a single transaction. So again, let's talk about distributing work between on-chain and off-chain components. So if we are using these random identifiers, how would I know if someone has challenged me? So a big map is not searchable through the blockchain node itself, but it does not need to be searchable. The reason we use indexers is that the indexer gives us that querying capability. Uh, the blockchain's purpose is to provide trust and transactionality. And everything that doesn't strictly pertain to trust and transactionality really belongs off-chain. So the if we're running an indexer, we can just use the indexer to list out all the games where I have been challenged, all the games that I have started. It can also quickly and easily give me a short list of the games where I can where I can withdraw money from, either because of a timeout or because I won or because they are a draw. So don't put features onto the chain that do not need to be on the chain. The reason a dApp is made up of on-chain components and off-chain components is so that the off-chain part can carry the brunt of the work, and the on-chain, the blockchain part can be only a secure and simple lock that does the job that it's supposed to do. So, John, would you like to take over for the summary?
I would. So yes, the summary, writing smart contracts requires a specialized approach. It's very different from any of the other kinds of programming that we do in our everyday lives. We have to ensure that everything is O1 memory and time. And one thing that we didn't necessarily talk about today is that often also means things like keeping running totals rather than adding things up when a number is required, keeping averages going across multiple calls rather than perform them when they're queried. There should be a focus in a smart contract on readability, security, and safety. It's very, very common when you write an important smart contract to hand it off to a third party for that third party to examine it, to check that it is safe and that it conforms to best practice and that it will exhibit O1 behavior under the most adverse of conditions. You should always be thinking, how will somebody be exploiting my contract? If I wanted to attack my contract, what would I do? If I can't profit by breaking up if I can't profit off breaking the contract, can I harm others by breaking it? Like this case where the contract was just shut down and all of the money was lost. If a solution feels like it's a bad user experience, then you need not worry so much because the user experience does not belong here. It belongs on the dApp, and the dApp has the luxury of working on your extremely powerful desktop computer or your phone, which is more powerful than a supercomputer from the 1970s. So always shift that functionality to the place where you can perform it quickly and cheaply, and where if you get it wrong, you can upgrade it. And finally, you should always have an indexer. If you want to know all of the games that are being played, you look in the indexer and you find all of the keys of the big map. You will not get that data on the chain, but you can query it off the chain.
Okay, and that is it. I have collected some resources here. These are the three main languages for writing smart contracts on Tezos, and all three have really good introductions and tutorials. And the final link is Kapasa, which is our indexer. It is a small-scale indexer that we developed to index a single or a small set of smart contracts. And I believe it is probably the well, I mean, I'm talking home a bit here, but it is probably the best solution in the Tezos ecosystem right now to writing a reliable, self-contained distributed application. And that is what we wanted to talk about. And I would like to open the session up for questions now because I'm confident that there are some.
I actually noted down some questions from earlier, which I just wanted to address really quickly. And one of them kind of relates to this. Someone asked, what's the difference between Solidity and Tezos smart contracts? And I mean, there are very many. But I think one of the most important is that the Tezos smart contract machine is a very, very, very strongly typed virtual machine, which means that it can be interrogated, and which means that you can examine the storage a lot more easily than you can with Solidity. So Tezos smart contracts are formally a lot more strict than Solidity ones, and they're a lot easier to examine and to reason about.
Yeah, so the an EVM smart contract storage is essentially a sparse, an unlimited size sparse array of 256-bit words. It's untyped, so looking at it, you just see like this tree of bits. It's in order to make any sense of it, you need to know the source code of the smart contract. With Tezos, the storage of a smart contract is a strongly typed record. So you can just look at the storage and you will have like some idea of what is going on there. But of course, like with Ethereum, you don't need to pay gas for the size of your storage. In Tezos, as we mentioned, you do, except for the stuff that's in a big map.
Cool. I think, does that address the question that Vasil asked? How is the map versus big map issue solved elsewhere, e.g. other chains?
Yeah, so on EVM, there is no such issue. The EVM does not perform deserialization operations when starting a smart contract. It just presents this very simple sparse array of memory, like virtual memory, to the code in the smart contract, and it can just randomly access it as memory. So there is no such problem there.
We have a good question. What about security? Are Tezos smart contracts more secure than those in Solidity? And I think my answer would be they can be.
Yeah, so
I mean,
like you can shoot yourself in the foot with the safest gun in the world. The way the Mikasan VM was designed was to make it easier to audit smart contracts. And of course, like with the strongly typed storage, it's easier to make sense of what is going on in a smart contract. So in a way, it's easier to get to be confident about whether a smart contract is safe to interact with or not. But inherently, it's a Turing complete virtual machine. It's equally easy to write unsafe code on it as on the EVM.
if proxy upgradable pattern is not recommended, how do you handle replacing the contract when it has assets? For example, Tez or NFTs?
You don't. You just don't. You have to get it right the first time. If you absolutely have to make a smart contract upgradable, then I would say you should use a DAO to handle the upgrade so that no single person can force an upgrade. But then, of course, the DAO has to be secure, and that's like a whole other can of worms.
I guess one thing one can also do is one can always copy the storage of a contract. So in the worst case, if I had a register of assets that I knew to be insecure, then I can copy the storage to a new contract and try and persuade everybody to use my new one rather than the old one. But this is not a very pleasant user experience.
Well, of course, then all the people who are using the old contract need to be able to withdraw their assets. And if there was like a breaking attack, like with the Parity wallet, then people might be unable to withdraw their assets from the smart contract, and that would be an issue. And there's just no good solution for that. Which is why you should always strive to make your smart contract as simple as possible. The more complicated it is, the easier it is for bugs to creep in.
I would like to congratulate Dani for making such an excellent job of this presentation under adverse conditions.
I think that I would second that. There is actually, did you cover Aaron's question about would you copy the storage manually?
Yeah, it's not very much fun to do this.
Not always feasible, because even though you can initiate a big map with a map when you're deploying a contract, if the storage is too big to be initiated, then it becomes a really, really hard thing to do. Like you would have to prepare the new contract to be filled up with like some kind of init operations separate from the deployment. So it's just not like copying the storage is not something that you should plan to do because it's not simple.
All righty. Any other questions, guys? Perfect. Dani, John, thank you so much for your time today, and particularly Dani with a, well, it sounds like a really bad cough as well. So it came across perfectly. So well done. But thank you very much for an excellent talk, excellent depth, and some really thought-provoking stuff as well, and particularly useful. For you as participants, we will have this go on YouTube and onto Medium tomorrow for you to enjoy this content again and use it for future learning. But in the meantime, again, thank you to our brilliant speakers, and we look forward to seeing you next week. Vanessa, what have we got next week?
I believe it's designed for dApps.
Yeah, it's UX practices for dApps and Tezos.
Oh, very good. Yeah, it is. I was going to say front end. I was like, is it front end or UX? Front end. It's UX. Awesome. Thank you very much, guys. Have a wonderful evening, afternoon, morning, wherever you are. And we will see you next week. Thank you very much.